Video 28 of the master course Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is the quantum mechanical expressions for the electric dipole moment. From the previous chapters, we have now three possibilities how to derive at the quantum mechanical expression for the electric dipole and quadrupole moments. Because we had definitions for the moments as integrals over the charge density, the first and second order moments of the charge density. In order to translate that to quantum mechanics, then we need a quantum mechanical expression for the charge density, which we actually also already had derived in chapter 2 of the book. The second option was that we derived that expression for the moments as derivatives of the interaction energy, the energy of the interaction of our molecule with external fields. In order to use that, we now, of course, need quantum mechanical expressions for the energy of a molecule in an external field. And then we could also go back to the Hamelin-Feynman theorem, which we derived in chapter 3 of the book, which shows that a derivative of the energy with respect to a parameter in the Hamiltonian can actually be also written or can be shown that it's the same as the expectation value of the corresponding derivative of the Hamiltonian. So we don't need an expression for the energy, we only then need the expression for the Hamiltonian in the presence of the field, which is what we had derived at the end of chapter 2. Let's start with the first version. Let's start with the expression of moments as integrals over the charge density. Right now, and in most of the book, we assume that we make use of the Born-Oppenheimer approximation, which means that we separate our problem in two problems. One, the electronic one, where we have the nuclei fixed at fixed points in space, and the electrons are moving. And that means that the nuclei have discrete nuclear charges, or the nuclei are discrete nuclear charges, which are located at fixed points. And then we have a continuous charge distribution of the electrons, which means the integral over the charge distribution, the first moment, which gives our electric dipole moment, we can split up in still an integral over the continuous charge distribution of the electrons here. And we just get, instead of the integral, we get a sum over all the nuclei with their charges, which are located at the points where the nuclei are. So we are fixed with that part, with the nuclear part, nuclear contribution to the electric dipole moment. For the electric part now, in order to translate this to quantum mechanics, of course, we need a quantum mechanical expression here for the charge distribution. And we had that already previously. We had the charge distribution here, charge density, as this expectation value of the density operator, and then multiplied, of course, with the charge of the electrons, which is minus the elementary charge. So we have this expectation value of the density operator. Now, if I insert that here in my integral over the first moment of the charge distribution, I have now sort of an integral within the integral, but there are different integration variables, because in this expectation value, of course, I integrate over all position vectors of my electrons, of my n electrons, whereas in this integral here, I integrate over all points in space, not related to electrons, but points in space. Now here I have the Dirac delta function, and the Dirac delta function up here is where I are the integration variables of this integral, and r is a fixed point. But the Dirac delta function is it's symmetric, and remember that if you integrate a function multiplied with the Dirac delta function over whole space, then you get the value of that function at the point of this argument of the Dirac delta function here, a or which is, I mean, the argument which is not the integration variable. So therefore, let's look at this here. First of all, we can interchange the order of the two integrations, which means we can move the wave function and the integral sign, I mean here the bracket notation, outside of my integral over the points in space. And then comparing with here my expression, the integration over a function multiplied with the Dirac delta function. Now my function then of course is this here, where the variable is r, or here the alpha component of r. So the variable r is r here, and I integrate over r, which means by doing the integration here, like the Dirac delta function, I'm going to replace my integration variable r by, here it's by a, and what is a? A here is the position vector of the electron I. So I'm going to, when I do the integration here over r with the Dirac delta function, I'm going to replace in my function here, which is this expression, I'm going to replace r here by ri. And then this integration over space is gone, and I'm just left with my expectation value, the integration over the position vector of all electrons, and here my function. So I'm going to get this integral instead of. And that is now an expectation value of this operator instead of what I had before. So my electric dipole moment is an expectation value over this operator here, which we then are going to call the electric dipole moment operator. And that's the electronic part. And here I have the nuclear part, which I just can simply calculate from the position of the nuclei and whatever charge they have. Correspondingly, I can apply the same transition to quantum mechanics to the expression for the second moment, or for the quadrupole moment. And I will end up at these expressions here, where again, I have two contributions. I have a nuclear contribution because I have the nuclei fixed in space at fixed positions. Okay. So I get this one here, or in the quadrupole moment, the little bit more complicated expression. And the electronic part, where I had the electronic charge distribution, I again insert the expectation value of the density operator for the electronic charge distribution and do the integration over all space with the Dirac delta function, and I get this expectation value here, where one could call this operator in the middle now the second electric moment operator, and this one here one could call the quadrupole moment operator. So far, so good. Now let's look at the second approach. The second approach was that we also had expression for the moments as derivatives, first derivatives of the energy of a molecule in the presence of an electric field. And now we will look at the permanent moments. In the following chapter, it becomes clear what the difference is, but yeah, the permanent moments, which means we will look at these derivatives evaluated at zero field strength. But in order to be able to evaluate these derivatives of the energy in the presence of the field, of course, we need an expression for the energy in the presence of the field. And there we can use now perturbation theory. We can look at use perturbation theory to get an expression for the energy in the presence of an inhomogeneous but otherwise time-independent electric field. And perturbation theory tells us that the first order correction to the energy, the one which is linear in the perturbation, is just can be calculated as the expectation value with the ground state, unperturbed wave function, and the first order correction Hamiltonian, or the first order Hamiltonian. Now, what is the first order Hamiltonian? For in the presence of an inhomogeneous electric field, well, it's the charge of our particles which we have, so in our case here, electron nuclei multiplied with the electrostatic potential due to this inhomogeneous but otherwise static electric field. Now the electrostatic potential we had actually derived in chapter 4.2 as a series expansion. And if you go take the first two terms, or actually the first three terms, and then ignore the constant term, then we get this one, where we have the electric field multiplied with the position vector of the particles relative to the origin, to the expansion point. And the next term was then where we had the electric field gradient, the derivative of the electric field with respect to x, y, z coordinates, multiplied with essentially the position vector of our particles squared. But again, the position vector always with respect to this origin. So inserting this expression, which is the expression 4.15 from chapter 4.2, in our expression here for the Hamiltonian, we can write the first order perturbing Hamiltonian this way, where we here have a term which depends on the components of the electric field, and here have a term which depends on the components of the electric field gradient. And then I split here the operators, the perturbing operators, into two parts. One which depends on the coordinates of the electrons, and here that is the O operators, and the omega operators with the Greek letter, which is depends on the positions of the nuclei. Because here I have the sum over electrons and nuclei, and correspondingly here for the two terms, the electronic and the nuclear term with respect to the electric field gradient. Now writing these operators out, the one, the perturbing operator for the electric field and the electrons obviously looks like this then. And this operator we will also call the electric dipole moment operator. That's the same operator as I just had a few slides ago in the expectation value. And correspondingly, this operator here looks like this. That's the one which is multiplied with components of the electric field gradient. And this can be called the electric quadrupole moment operator, or I can write it as 1 over 3, 1 divided by 3 times the electric quadrupole moment operator. And correspondingly for the nuclei, the only difference is that instead of electronic coordinates here, I have now nuclear coordinates. Now for the permanent electric dipole moment or the electric quadrupole moment, that's of course expressions which do not depend on the field strength then any longer, because it's a permanent one, and therefore in the derivative here I only need to take the derivative of the first order correction to the energy, the term which is linear in the field or in the field gradients here. So now using my expression for the first order energy correction, which is the expectation value of the first order Hamiltonian, I have to take these two derivatives. Before I look at that, let's squeeze in the alternative definition from the Hermann-Feynman theorem. There, the Hermann-Feynman theorem says that a derivative of the energy with respect to a parameter in the Hamiltonian, like for example the electric field here, can be calculated alternatively as the expectation value with here the unperturbed wave function of the corresponding derivative of the Hamiltonian. Now here's the full Hamiltonian, whereas here I had the first order correction to the Hamiltonian. However, as we are dealing with electric field perturbations, and the electric field only enters in the Hamiltonian in one term, in a linear term, the derivative of the full Hamiltonian or the derivative of that linear term, the first order correction to the Hamiltonian, is of course the same. And so if I take the derivative with respect to a component of the electric field, I get the corresponding components of the electric dipole moment operator, here the electronic part and here the nuclear part. And correspondingly, if I take the derivative of either the full Hamiltonian or the first order correction to the Hamiltonian with respect to a component of the electric field gradient, I get the quadrupole moment operators and inserted in my expectation values. Now I get the same quantum mechanical expression for the electric dipole moment or for the electric quadrupole moment as we had derived before in the first derivation, where we started with the integral expression for the moments and replaced the electric density with the quantum mechanical expression. So both derivations lead to the same expression at the end. And this fact that we get as derivative of the energy or with it directly as expectation values, we get the same expression. That holds as long as we're dealing with the exact wave function. Later on, when we come to the third part of the book, we will see that for approximate wave function, this does not always hold.